In the ever-expanding landscape of theoretical physics, Jonathan Oppenheim's post-quantum gravity theory emerged as one of the most intriguing and controversial ideas of 2024. This bold framework aimed to reconcile the seemingly irreconcilable, the chaotic unpredictability of quantum physics, with the deterministic elegance of gravity. While the theory captivated the scientific community, a growing consensus suggests it may soon be disproven. A recent paper proposes a groundbreaking experiment that could deliver the verdict. At the heart of the problem lies a cosmic paradox. Quantum physics thrives on randomness and uncertainty, where particles exist in superpositions and outcomes are probabilistic. Gravity, on the other hand, operates with deterministic precision, shaping the universe in predictable ways. Yet these two forces must coexist. Quantum particles, after all, exert gravitational effects. For decades, physicists have sought to unify these frameworks into a single theory of quantum gravity, but the challenge has proven monumental. Traditionally, quantum gravity theories attempt to quantize gravity itself, imbuing it with quantum properties. Oppenheim, however, flipped the script. His theory proposed that instead of making gravity more quantum-like, we should embrace its classical nature and inject randomness into gravity to align it with the quantum world. This unorthodox approach suggested that gravitational randomness could even eliminate the need for dark matter, one of physics' biggest mysteries. While most quantum gravity theories remain frustratingly abstract and difficult to test, Oppenheim's idea offers a unique advantage. It makes predictions that could be experimentally verified. His framework implies that gravitational randomness would introduce small, measurable fluctuations in the masses of objects. These fluctuations, if observed, could provide evidence for the theory. Conversely, the absence of such effects could rule it out. A recent paper takes this idea one step further, proposing a specific experimental test. If gravity remains non-quantum but gains randomness, it would behave in unexpected ways, creating fuzzy gravitational attraction. This fuzziness would, in turn, amplify quantum uncertainty in small objects. By observing these subtle effects, scientists could uncover whether Oppenheim's post-quantum gravity holds up or crumbles under scrutiny. The proposed experiment is as imaginative as the theory itself. It involves two pendulums, meticulously designed to detect gravitational randomness. If Oppenheim's theory is correct, this randomness would manifest as a greater spread in the pendulum's mass positions, albeit at scales that push the limits of detection. The challenge lies in the minuscule size of the effect, which demands extreme precision. Researchers would need to conduct the experiment at ultra-low temperatures to minimize thermal noise and use advanced techniques to reduce other sources of interference. Ultimately, the sensitivity required might even push the experiment into the realm of space-based labs. Adding to the pressure on Oppenheim's framework, a new mathematical theorem suggests that leaving gravity classical, without quantization, would disrupt the delicate structure of quantum physics in a way that can be tested. This connection between classical gravity and quantum disruption strengthens the case against post-quantum gravity. It hints that Oppenheim's theory, while creative, may simply be too random to reflect reality. In a humorous aside, the speaker likens post-quantum gravity to postmodern art, suggesting it might be too random to make sense. Yet, even the most skeptical scientists acknowledge the value of being wrong. It's through disproving ideas like Oppenheim's that physics edges closer to the truth. Whether the experiment confirms or refutes the theory, it represents a crucial step in our quest to unify the quantum and gravitational realms. Oppenheim's theory may be on shaky ground, but its boldness has reignited the search for answers to some of the universe's most profound questions. If nothing else, it serves as a reminder that science thrives on daring ideas and the willingness to test them,